Okay, so understanding logs. Logs is actually not that difficult once we understand the relationship. And we'll talk about Euler's number or Euler's number also. So remember, when it comes to any exponent, there's a base value and the exponent. So in 2 to the power 4, 2 is the base and 4 is the exponent. Okay, 2 is the base right here and 4 is the exponent. Next thing to point out is what exactly is Euler's number? So as we move forward using natural log, what does that all mean? Well, if we just said pi, instinctively you know pi is 3.14 ... Euler's number is just another representation where the symbol pi means 3.14. When you see E for Euler's number, it's 2.718 ... It keeps going. So just remember, pi Euler's number, very similar. It's just a way to express a specific number with a symbol. Okay, so again, we're just expressing a number with a symbol. So when we use the exponent function, we're saying base, remember right here, base, the 2. The base now is, rather than 2, we're saying base of 2.718 ... to the power of whatever number. So when we do that 2.718 to the power of 1, we obviously get that number. So we're saying an exponent, or Euler's number, to the power of 1, we get 2.718. Now, if we square that number, so then we say is equal to this amount to the power of 2, look what we get. And so when we use the exponent function in Excel, we're saying 2.718 to the power of 2, and that's what we get. Now it's 2.718 to the power of 3, so on and so forth. So it's the base relative to whatever power. So that's why you see here e to the power of is e to the power of 1, 2, 3, where e, or Euler's number, is 2.718. We could replace the e with pi and then just say pi to the power of 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's what the exponent function is doing. It's recognizing Euler's number as the base to any power. We can also then get the inverse of this value by using the natural log. And also, so you just see here we have 2.718, that is Euler's number here, the power of 1, the power of 2, and so forth. And just notice that the column here, F, when we take the 2.718 ... to the power of 1, 2, 3 through 8 is equivalent to using the exponent function. These two are identical, okay? Now we'll get to natural log, we'll come back to that, but let's first start with what's called log base 10. So log base 10 is this idea that, well, if the base number is 10, then what is the exponent that describes that relationship? So if we had 2 to the power of 1, we'd have 10. 10 to the power of 1 is 10. 10 to the power of 2 is 100, and so forth. And so obviously we're just adding a 0 each time. So when we do log base, what we're saying is, well, what's the relationship where if the base value, again, remember here, we're 2 base to the exponent of 4. So we're saying now it's 10 to the power of what? So what we're saying here, when the value is 1, we're saying, well, if the base is 10 and our value is 10, that means it must be to the power of 1. And that's what you see here. When we have our value of 100 and the base is 10, that must mean it's to the power of 2. So normally we're used to describing base values, and now what we're getting into is understanding what exponents would be. So we're getting into the nonlinear side, okay? So we're used to being on the linear side, now we're talking about nonlinears, specifically the exponents. So when we use log base 10 of 5, what this is really saying is, well, this value is 10 to the power of 5 right here. And so if the base is 10, what describes this value? Well, it's 5. And that's what you see here. So it's just explaining this relationship. So notice here, log base is the 10, and then we end up with 1 through 8. Now notice, again, if base is 10 to the power of x, so we have 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so the 3 is just the relationship between all these. So hopefully that explains what log base is. So we could have the base be 2, 3, 4, 5, whatever number we pick. Now what happens if the log base is actually 2.718? That is, what if we use Euler's number as the base? Well, that ends up being the natural log. So we're saying, well, if 2.718 is the base number, remember again here, remember 2 to the power of 4, 2 is the base. So it's like saying 2.718 ... to the power of whatever number, 2.718 is the base. So if we have a number like 2.718 and we take the natural log of that number, well, 2.78 to the power of 1 gives this relationship. Now notice if we have a value 7.389 ... and we take a base value of E, or Euler's number of 2.718, we get a value then of 2. Why? Well, it's equivalent to what? E to the power of 2. And so all we're saying here is, well, if the base is E, then what must the exponent be in order to get that value? Okay, so we're just describing a relationship here between the base, the exponent, and the value that we currently have. That's it, nothing more. We can also use the log function in Excel, where we say, well, if we have a log of this value and we use F6 as the base, what must the value be in terms of the exponent? And so we can go down here to form. What we see is, well, if we use a log function where the base is 2.718 ... and the value is 54.958, what must be the exponent if this is the base in order to get this value? There you go. Now what if we had some different value like 70? Well, we would just simply say is equal to the log value of this. So we're saying now, again, if the base is 2.718, what must the exponent be so that we get a value of 70? And so 2.718 ... to the power of 4.2484 ... gives us a value of 70. And how do we know that? Well, we can just simply say is equal to the exponent of this number, and we get 70. So all we're doing is just describing a relationship between the value that we observe, the base value, and the exponent that gets us to that observed value. So hopefully that helps.